In this section, we're going to be talking about absolute convergence, the ratio test, and the root test. So given any infinite series, so the sum as n goes from 0 to infinity of a sub n, so a1 plus a2 plus a3 dot dot dot, we analyze the related series, the sum as n goes from 0 to infinity of the absolute value of the an's, which would be the absolute value of a1 plus the absolute value of a2 plus dot dot dot. If the series of the absolute value of the terms converges, then we call the series, the original series, absolutely convergent. So determine if the series is absolutely convergent. So we look at our an, which is this. So our an in this case is negative 1 to the n all over 3 to the n. So then the absolute value of an is going to be the absolute value of negative 1 to the n over 3 to the n, which is just going to be 1 over 3 to the n. So putting all that together, the absolute value of an is 1 over 3 to the n. So now the question becomes, does the series of the absolute values converge? So in this case, that's the sum as n goes from 0 to infinity of 1 over 3 to the n. And the answer to that is going to be yes, because it's geometric with r equal to 1/3. So then the series is absolutely convergent. All right, so let's take a look at the next example. So once again, we identify our an, and it looks like I have a typo here. Negative 1 should have been in the exponent, so I have a sub n is equal to negative 1 to the n minus 1 all over n. If I take my absolute value, I get the absolute value of an is going to be 1 over n. And this is the harmonic series. And the harmonic series is known to diverge. We could also note that it is a p-series with p equals 1, which gives us the same conclusion that the series diverges. So this leads to another definition and a theorem that goes along with it. We say that a series is conditionally convergent if the original series converges, but the absolute values of the terms of the series diverge. And then we have a theorem. If the series of the absolute values converges, then the original series must converge. So, in the previous example, B, that is an example of a conditionally convergent series because it's the alternating harmonic, and the alternating harmonic series indeed does converge. So determine if this series converges. So our an this time is equal to cosine n all over n squared. So this series has both positive and negative terms. But does not alternate. So if we look at the absolute values of our ANs, so the absolute value of AN would be the absolute value of cosine n all over the absolute value of n squared, which is just the absolute value of cosine n all over n squared. So we make a couple of observations that 0 is less than or equal to the absolute value of cosine n, which is always less than or equal to 1. Dividing this inequality by n squared yields the following relationship, that 0 is less than or equal to the absolute value of cosine n all over n squared, which is less than 1 over n squared. So then we'll notice that we have the following. So by comparison, the sum as n goes from 1 to infinity of the absolute value of cosine n all over n squared is less than or equal to the sum as n goes from 1 to infinity of 1 over n squared. This is a p-series. P equals 2, so it converges. So the series as n goes from 1 to infinity of absolute value of cosine n over n squared converges. By comparison, which means that so the original series sum as n goes from 1 to infinity of cosine n over n squared is absolutely convergent. Which implies convergence. So, if we rearrange the order of a finite sum, the sum is unchanged. And that's just the commutative law of addition, which says that the order that we add things in doesn't matter. So, for instance, 1 plus 2 plus 3 is the same as 2 plus 1 plus 3, which is the same as 3 plus 1 plus 2. A rearrangement of a series is a new series with the order of the terms changed. And then we have a theorem that says if a series is absolutely convergent with some n, s, then any rearrangement also has some s. Alright, so let's take a look at an example of this. So the alternating harmonic series is conditionally convergent. So it can be shown, and we'll do this later, negative 1 to the n plus 1 all over n, which equals 1 minus a half plus a third plus a fourth, or minus a fourth, plus dot 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 on forever, adds up to the natural logarithm of 2. So if I were to take this equation right here and divide both sides by 2, that would give me the new series 1/2 minus a fourth plus a sixth minus an eighth plus dot 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 on forever equals the natural logarithm of 2 divided by 2. So if I then take this series and I'm going to line up this first bit, so 1 minus a half plus a third minus a fourth plus, I'll write out a few more terms, a fifth minus a sixth plus dot 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 dot, and that equals the natural logarithm of 2. So then if I add this series to it, I have 1/2 minus a fourth plus a sixth minus an eighth and so forth equals the natural log of 2 over 2. If I add these two series together, every other one of these is going to reduce out, and that leaves 1, and then I'm going to get plus a third. Negative fourth minus a fourth gives us negative 2/4, which reduces to 1/2 plus a fifth. Those cross out, and so forth. If I keep going, my next one would be plus a seventh. And then we would have minus an eighth and minus an eighth, which would give us negative 1/4 and so forth. And then that would equal natural log of 2 plus natural log of 2 over 2. So that would be 3 natural log of 2 over 2. Well, this creates a bit of a problem because that's 1 plus 1/3 minus a half plus a fifth plus, there's our fourth, and a seventh, and then a sixth, and so forth. We keep doing this. This is a rearrangement of the harmonic series, or the alternating harmonic series, which we know equals the natural log of 2. And it has a different sum. So turns out that in order for us to have all of the nice properties that we're used to having with finite sums for addition, we have to have absolute convergence. If a series is only conditionally convergent, if we rearrange the terms, we will change the sum of the series. So that is, the sum depends on the order of the terms. All right, so then the next thing we need to look at is we want to take a look at two of our tests, and those are the ratio test and the root test. And these are right here on our sheet. They're the last two. So we have the ratio test and we have the root test. So the ratio and the root test are two different ways for us to look at series. So the nice thing about both of them is they tell us about absolute convergence. So if we're given any series, for the ratio test, we take the limit as n goes to infinity of the absolute value of the ratio of the next term over the previous term. And if that limit in absolute value is less than 1, it converges absolutely. If the limit is greater than 1, the series diverges. And if the limit equals 1 exactly, the test fails. And we have to use a different test. The root test is similar, but now we take the limit as n goes to infinity of the absolute value of the nth root of a to the n. And if this is less than 1, the series converges absolutely. If it is greater than 1, the series diverges. And similar to the ratio test, if it equals exactly 1, that means the test fails and we have to do a different test. So let's go ahead and take a look at our next example. So test for absolute convergence. So we have our an is -1 to the n cubed over 3 to the n. And we need to evaluate the limit as n goes to infinity of the absolute value of an plus 1 all over an. So we take the limit as n goes to infinity of the absolute values of these. So that's going to be -1 to the n plus 1, n plus 1 cubed all over 3 to the n plus 1 divided by -1 to the n cubed all over 3 to the n. So in absolute value, the -1s will only become a factor of +1 and they reduce out. We then have a fraction divided by a fraction. So we're going to multiply by the reciprocal of the denominator. And that's going to give us n plus 1 cubed over 3 to the n plus 1 times 3 to the n all over n cubed. I'm going to drop the absolute values here because all of the terms are positive and they're no longer needed. So we start reducing, and 3 to the n plus 1 divided, or 3n over 3 to the n plus 1, the n's reduce out. So in the denominator, we're going to leave behind 3. And then I'm going to have an n plus 1 cubed all over n cubed. So now there's a few different ways we can do this. So we have the limit as n goes to infinity. The 3 comes out of the limit, and we're left with n plus 1 cubed over n cubed. So we can break this up using algebra and write that as n plus 1 times n plus 1 times n plus 1 all over n over n over n. And then that would reduce to 1 plus 1 over n times 1 plus 1 over n times 1 plus 1 over n. And as n goes to infinity, each of these will go to 0. 0 and 0, so 1 times 1 times 1 is 1. So we get our limit is 1/3 times 1, which is 1/3. So if that's the case, then by the ratio test, the series is absolutely convergent. All right, let's take a look at our next example. We have the sum as n goes from 1 to infinity of n to the n over n factorial. So we're going to try the ratio test again. We have a sub n is n to the n all over n factorial. So we take the limit as n goes to infinity, and both of those are always positive, so I'm not going to put on the absolute values. So a to the n plus 1 is n plus 1 to the n plus 1 all over n plus 1 factorial all over n to the n over n factorial. So we have the limit as n goes to infinity, and I said I wasn't going to put them on, and there they are. So let's multiply by the reciprocal of the denominator, and that gives us n plus 1 raised to the n plus 1 all over n plus 1 factorial times n factorial all over n to the n. So let's simplify up and rearrange some of these. So I'm going to have n plus 1 raised to the n plus 1, and I'm going to have an n to the n. And I'm going to group those together. So this is going to be n plus 1 to the n times n plus 1, splitting up that exponent, over n to the n. And then I'm going to group together the other two terms, so the n factorial and the n. So here I get my n factorial, and in the denominator it's going to be n plus 1 times n factorial. So a couple of things reduce out. The n to the n, or the n factorial and the n factorial reduce out. And then we also have that the n plus 1 here reduces out with the n plus 1 here. And now we're left with n plus 1 to the n over n to the n. So we can combine these together. So the limit as n goes to infinity, and rewrite that as n plus 1 over n, all raised to the n. And we need to determine if this converges. So by termwise division, we take the limit. That's going to be 1 plus 1 over n raised to the n. And if you remember back to Calc 1, this actually converges to the number e, but let's see why. So let's suppose that this equals the limit L, and then if we take the natural logarithm of both sides, we would have n natural log of 1 plus 1 over n is equal to the natural logarithm of L. And the limit as n goes to infinity is going to be infinity times the natural log of 1, which is 0. So we rewrite this as the limit as n goes to infinity of the natural logarithm of 1 plus 1 over n divided by 1 over n. And now this is of the type 0 over 0. So by L'Hopital's rule, we take the derivative of both the numerator and the denominator. And the derivative of the numerator is 1 over the inside, so 1 over 1 plus 1 over n times the derivative of the inside, which is going to be negative 1 over n squared, divided by the derivative of the denominator, which will also be negative 1 over n squared. Luckily, those two things reduce out, and now when we take the limit as n goes to infinity, the 1 over n goes to 0. So then we get 1 is equal to the natural logarithm of L. Solving for L, we get e to the 1, which is just e. And e is bigger than 1, so the series diverges. So remember, for convergence, the limit had to be less than or equal to, or just strictly less than, not or equal to 1. Alright, let's take a look at our next example. So for this one, we're going to want to use the root test. So once again, we identify our a sub n, and for the root test, we take the limit as n goes to infinity of the nth root of a to the n. So in this case, that's the limit as n goes to infinity of the nth root of 2n plus 3 over 3n plus 2 raised to the n. The nth root and the nth power here are inverses, so this and this reduce out. And we're left with the limit as n goes to infinity of 2n plus 3 over 3n plus 2. So that's type infinity over infinity, or we can just factor out an n, either way you want to do it. So by L'Hopital's rule, that would be the same as the limit as n goes to infinity of 2 over 3, which equals 2/3. 2/3 is less than 1, so the series is absolutely convergent. Alright, so now it's your turn. You go ahead and do the U try. So we have the sum as n equals 1 to infinity of 5 to the n over n factorial. Alright, so for this one we're going to use the ratio test. I take the limit as n goes to infinity of 5 to the n plus 1 over n plus 1 factorial all over 5 to the n over n factorial gives us the limit as n goes to infinity of 5 to the n plus 1, which I'm going to do 5 to the n over 5, and then I'm going to do n plus 1 times n factorial times the reciprocal of the denominator, which is n factorial over 5 to the n. So now, a whole bunch of things reduce out. Those reduce out. Those reduce out. And we're left with the limit as n goes to infinity of 5 over n plus 1. So a constant divided by infinity equals 0. So we're going to have that our series converges. For our last example, we want to use the ratio test on this as well. But before we get started, we'll notice that this is a little bit different. Besides having n's, this also has a variable x. So we're going to start with the limit as n goes to infinity of, and we're going to have our -1 to the n plus 1, x to the 2 times n plus 1 plus 1 all over 2 times n plus 1 plus 1 factorial all over -1 to the n x to the 2n plus 1 all over 2n plus 1 factorial. So once again, the absolute values of a power of -1 are just going to be 1. And let's start by multiplying by the reciprocal and cleaning up some of our stuff. So 2 times 2 to the n plus 1 is 2n plus 2 plus 1. So that's going to be x to the 2n plus 3 over, and then that's going to be 2n plus 3 factorial times our 2n plus 1 factorial all over x to the 2n plus 1. So expanding some of these terms, we're going to have x to the 2n plus 1 times x squared, and then expanding our factorial, that's 2n plus 3 times 2n plus 2 times 2n plus 1 factorial times 2n plus 1 factorial all over x to the 2n plus 1. That reduces out, Our 2n plus 1 factorial and our 2n plus 1 factorial reduce out, and we're left with the limit as n goes to infinity of x squared all over 2n plus 3 times 2n plus 2. So now we need to take this limit. Turns out in this case that we need this to be less than 1. So for any value of x, the limit as n goes to infinity, so for any fixed x, this is going to be a constant divided by infinity, so this is going to be 0 is less than 1. So the series converges for all x.